Right, welcome to week 9, Sets and Dictionaries, in which we introduce, surprise, surprise, sets and dictionaries. So just to recap a little bit, you're familiar with lists and tuples. So using my own examples over here, I can have numbers as a list of numbers, 10, 20, 30, and that's a list. And I can have a point, which is a tuple, which kind of looks similar. This is some point maybe in three-dimensional space. In either case, there is an in operator that I can use to ask if something's present in the sequence of numbers. So I can say, I can ask, for example, is 10 in numbers? This is an expression which evaluates to true because 10 is in numbers. I can ask, is 40 in point? And it evaluates to false because 40 isn't in the point. The big difference, of course, between numbers and lists and tuples is that lists are mutable. You can modify the elements and sort them, things like that, append to the end, whereas tuples aren't. For now, all I want you to focus on is the idea that both of these have an in operator to check if something is inside the collection or sequence. How does it do that? I guess it's fairly obvious how it does it. If you ask, is 40 in numbers, it says, let me see, is 40 equal to 10? No. Is 40 equal to 20? No. Is 40 equal to 30? No. Oh dear, we've got to the end of the list. 40 isn't in numbers. That's what we call a linear search. And that's that word there in this example slide. You can type that one into your computer if you like. Linear search is what we call, fancy mathematical notation, you'll do a lot more of this in COSC 122, is big O n, meaning it takes order of n, where n is the number of elements in the collection, in order to answer the question how many, not whether something is present in the list. So this in operator is big O n. That has some serious implications. And here's an example. I'm going to develop a program, I've already started, to count the words in the complete works of Shakespeare. So I have a file, a text file, which happens to contain the complete works. There it is. I read it in and convert it to lowercase. So that's a single string in the variable text containing the entire complete works of Shakespeare. I split it on white space and I print out the first 1,000 words. This is a standard thing you've done in COSC 121 to define a word as the stuff between white space. Not a very good definition in the context of the complete works of Shakespeare. So we get words that patently are not words, like 10, that isn't a word. Commits full stop is not a word. The full stop doesn't belong inside that word at all. So it's not a very good definition. It's one that normally is good enough for COSC 121, but I wanted this to be a realistic definition, so I cheated. I cheated by telling you something or showing you something you're not really expected to know about, which is regular expressions. Now please don't panic, these are not in the curriculum, you won't be tested on these, but I thought it might be fun to show you them anyway. I've imported the regular expression package and I've called a method inside it called findAll, which finds all occurrences of a substring defined to be the characters any one of the characters A through Z, followed by 0 or more of the characters A through Z plus hyphen or minus. Details don't matter. Let's not get too upset by them. There's the result of printing, and it looks kind of plausible, right? The Sonnets by William Shakespeare. From fairest creatures we desire, etc. We desire increase. I don't know. That looks like the complete works of Shakespeare, right? I just wanted to do that so we had a realistic exercise to play with. Now, how do we count them? The unique words, that is. To do that, I have to go through each word and check if it's in the unique words, right? So I go unique is the empty list, and I hope many of you, most, would be able to do this. I'm not sure. We'll find out maybe. For word in words, for each word, I'm going to see if it's in the unique list already. Have I found this word? If the word is not in the unique list, I haven't found it yet, I'm going to stick it on the end of the unique lists. Unique words list. When I'm done, I'm going to print how many there were. So I'm going to print the len of the unique words. Oh dear, unique words found. Sigh. And then I might as well print them. What the heck? Print the unique. So there's the list of the unique words. Let's see what happens. Right, we found, as before, 901,000 words, and now we're going through this piece of code to see how many of them are unique. So this didn't take long, right? That was over in less than a second, but now we're stuck in the piece of code here which says for each word, if it's not in the unique word list, add it to the unique word list. Now, coming over here, remember, asking the question, is something in a list, requires checking it against each element, which is, as we said here, of order n, where n is the size of the list. So if there is, say, 10,000 unique words in Shakespeare, well, we'll find how many there are because it just finished. We find that there are 30,699 unique words, and what we had to do was we had to look up each one of the nearly 1 million words in that list. So we had something like of the order of 30 billion lookups to do, and it took a while, right? Okay, well, you'd think we can't do any better than that. It's inherently a complex, slow operation. But wait, I'm going to make a small change. I'm going to put, instead of unique being the empty list, I'm going to make it the empty set. And I'm going to leave that unchanged. And instead of appending it, I'm going to add it, because it turns out that that's what I have to do to add an item to a set. So I set up a set of empty words. For each word, if it's not in the set, I add it to the set. Trivial change to the program, bingo, done. So now we have the same program running, same number of words found, but it was over in a fraction of a second versus 30 odd seconds. So hopefully you thought, wow, that was pretty amazing. How could you possibly do that? Isn't that an exciting question to ask? Well, watch the next video to find out, because that's all I'm going to show you in this video. Thanks for watching. Bye.